All right, ladies and gentlemen. Ladies and gentlemen, I feel compelled to tell you that class recording has begun. So if you do anything stupid, it will be recorded for posterity and posted on the internet. So don't do anything that you wouldn't want your mom to hear you do. So, all right, yesterday we started in on chapter 2, and I mentioned to you yesterday that chapters 2 and 3 deal with kinematics. So, yesterday I described kinematics briefly. Anybody remember our description of kinematics? Describing motion, but not telling about why, right? So we know this motion is occurring, and all we're doing is describing that motion without any regard to why it's happening, or how it's happening, or what's affecting it. We're just describing the motion. And when we talk about kinematics, I mentioned to you that there are 4 questions that we look to answer. So, Jill, what's one of the questions? Where? Where is this object? That's one question that we want to know about this object. What else?
What is it doing right now?
Okay, we'll go with, just to shorten it up, Anna, we'll go with what, right? So what is it doing right now, right? Next question? What next? What's going to happen to it in the future? And the last one, when? So when are all these things happening? And if we can answer those 4 questions, we do a good job of describing the motion. That's the gist of kinematics. So yesterday, we started talking about the first question. We started talking about where. The answer to that question is called what? What do we call where an object is? It's, well, we give it another word besides location. Position. Okay, so that answer to that question of where we call position. And in the process of introducing position, we also introduced an important concept that is essential if we're going to accurately describe that position, and that concept was what? The coordinate system. 2 parts to our coordinate system. If we're going to define a coordinate system, what do we have to do? A reference point, which is the origin, okay? And then what else do we have to do? So we got a reference point, and then what else? The initial and final position is more where an object is specifically, not the coordinate system itself, right? So the reference point, and then what else? In one-dimensional motion, what do we have to distinguish? Direction, right? So a frame of reference or a coordinate system has to tell us 2 things. So I should go here. So, as it says in your packet, right, the coordinate system defines an object's position. So in our coordinate system, we really should include 2 things. One thing is a reference point or an origin, and the other thing is a directional system. How can we tell one way from the other way? We talked about yesterday that we're going to start off with just one-dimensional motion. One-dimensional motion means what?
Just going like
either forward or backward or along what? A straight line, right? So we only have 2 choices, left or right. And we distinguish left or right by positive or negative, just like a number line. Okay? Good there. All right. We also started talking about now, so position is basically just where an object is. But then we started getting into a little bit more, okay, what happens if it changes where it is? And there's 2 ways we can describe the changing of an object's position. Pick one of them and tell me about it. Go ahead. So I'm sorry. Let me ask the question again. Okay, so yesterday, after we described position, which is where an object is, we talked about defining when an object is changing its position, when it's going from one place to another, right? Because if everything just stays in the same position, that's really boring. Nothing happens, right? But we talked about when things are changing. So I said we talked about describing changing an object's position in 2 ways. So I want you to pick one of them and then go. So Jill, pick one of them.
Distance.
Distance. What is distance tell you about an object's motion?
Like how far you've like done something.
Okay.
Or
Well,
like, yeah.
good. Alright, so let's go here, and if I remember right, I think it's page 44. 44R. 44. Okay. So as it says in your book and also in your packet, I think at the bottom of the first page, distance is the length traveled. The distance is the total length of the path that you take from one point to another point, without regard for the direction that you're going. So all we're doing is just adding up the length over and over and over and over and over again. Okay? The other thing that we talked about yesterday was what? What was the other description? Displacement. Also, when we talk about displacement, what are we concerned with?
Like where you end up and like where you start.
And where you end up or versus where you start. Or, as we define it here on page 45, the change in the position. All we're concerned about is where you start and where you finish. Okay? Good there. All right, let's talk about these terms a little bit more. Let's go here. All right. Move this here. And page. Okay, so distance. Distance is our first example. Distance is our first example of what we call a scalar quantity. It's not a scalar, it's a scalar. Okay? A scalar quantity only tells us the magnitude of a measurement. So when we talk about the magnitude of something, what does that mean? How big it is, or how much of it there is, or something like that. Distance is a scalar quantity. It only tells you how far you went, without regard for direction, right? We just keep adding distance. Doesn't matter whether we're going north, south, east, or west. We just keep adding up the distance. The odometer on your car, right, that shows up under the speedometer that calculates mileage, that just calculates distance. It doesn't matter which direction you go, it just keeps adding miles onto your car, regardless of the fact that this morning when you left your house, you started in your driveway, and sometime eventually today, where are you going to end back up? In your driveway. So over the course of your day, what's your displacement?
Zero.
What's your displacement? Zero, because what's your starting position versus your ending position? The same. But if we calculate your distance or measure your distance, you may go lots of places during the day, regardless, but still you may end up right back where you started. Okay? Displacement, on the other hand, we'll go green, please. So that's a terrible green. You guys can really read that thing.
It hurts my.
It hurts your eyes. We'll go purple. Alright, so displacement is a vector quantity. Okay? So a vector, oh sorry, go ahead.
No, no, it's okay. I'm like getting confused on like the time of vectors, like you said that you end up back in your driveway. Well, what's like the time period? Because eventually you're going to end up in your driveway.
Okay.
So
Right now, we're only dealing with which of the four kinematics questions?
right now.
Sorry. In section 2.1, we're only dealing with which of these four questions? Where? Time is not entered into this discussion yet. Okay? Time went to the discussion tomorrow. All right? Right now, all we're talking about is where, regardless of how long it takes or how much time passes between beginning and end. We're just talking about where. Okay? Time will start entering into this discussion. Okay?
Thank you.
All right. So, displacement is our first example of a vector quantity. A vector quantity tells us two things. Do you remember the two things that vector quantity tells us? Magnitude and direction.
What do you mean magnitude?
Well, we said that magnitude tells us what about a number? How far or how big or how much of something there is, okay? But sometimes that's not enough, okay? For example, Allison, let's say that the library is a mile away from your house. Is that enough really to tell or figure out how to get from your house to the library? No, because it's only telling us magnitude. It's only telling us how far the library is away from your house, right? In theory, it could be any spot that is 1 mile away from your house, so a circle with a radius of 1 mile. But that's not helpful a lot of times because it doesn't tell us exactly where something is. So if we say that the library is 1 mile southwest of your house, right? Now, including both the magnitude and the direction, that gives us a better description of where something is. Does that make sense? Okay. So vector quantities tell us magnitude and direction. Depending on what we want to know, sometimes we need both. Sometimes we only need one. Sometimes we only need magnitude, right? But other times we might need that direction as well, okay? For example, if you have your book open, look on page 46. And I believe you have these pictures at the top of page 3 of your packet as well, okay? So on page 46, up at the top, there is a lady who is, let's go jogging, because it doesn't really look like she's digging that hard. So. All right, in picture A, she runs within the coordinate system, starting at her initial position of 2 meters and ending up at her final position of 6 meters. In picture B, she starts for a second trip with her initial position at 6 meters and her final position at 4 meters. Question. Distance traveled for both of her trips is going to be what? 4 meters. Because distance is a scalar quantity. It only tells us what? Magnitude. How much? In both cases, she's traveling 4 meters. But there is a distinct difference between trip A and trip B, isn't there? That being what? The direction that she's going, right? So we have to have a way to distinguish one direction from the other. That's part of our coordinate system, right? We can distinguish one direction as positive, the other direction as negative, okay? Now, if we look at the formula or the equation for calculating the displacement of something, right? Going back to page 45, which I think is on the previous page of your guys' packet. I think it's on page 2 of your packet. We define the displacement of something as a change in its position. Delta x equals x final minus x initial. The difference between where something starts versus where something finishes. Depending on the numbers that we plug into that equation, we might end up with a positive answer and we might end up with a negative answer. Also, go ahead.
So you know how you said that displacement is like magnitude and direction?
Yes.
So the direction part is if it's positive, it means that they went in like the positive direction versus the negative.
Yes.
So that's what tells us the direction.
Exactly.
Okay.
Now, not to confuse you, but just to make sure that we understand, okay? The first term that we introduced in this chapter was position, right? And position tells us where something is. Okay? In picture A, right, she starts 2 meters to the right of the origin, or the reference point. And according to our coordinate called the right to positive direction. So her initial position would be positive 2 meters, because she started 2 meters to the right of the origin. Her final position would be positive 6 meters, because she ended up 6 meters to the right of the origin. Good? Going back to our formula for displacement, right? X final minus x initial, 6, positive 6 minus positive 2 gives you positive 4. Right? Meaning that if her displacement is positive, she went in the positive direction. Okay? In part B, picture B, her second trip, her initial position is positive 6 meters. 6 meters to the right of the origin. Her final position is positive 2 meters. 2 meters to the right of the origin. If we use those numbers and plug it into the displacement equation, okay, final minus initial, 2 minus 6 gives us what? Negative 4. Okay? Meaning that she went in the negative direction. Now, she's still on the positive side of the origin, but she's traveling in the negative direction. Position tells you where something is. Displacement will tell you how you're traveling. Does that make sense? We can still be on the positive side of the origin, but traveling in the negative direction. Or we could be on the negative side of the origin and traveling in the positive direction. Position tells us where we are currently. Displacement tells us which way we're going. Yeah, go ahead.
Are we ever gonna not use this back and forth?
Eventually, yes. Eventually we'll get to 2 dimensions.
Okay.
That the concepts stay the same, but how we mathematically define them is a little bit different. So that's why we start in 1 dimension and introduce the concepts, then go to 2 dimensions. This idea of positive position, negative displacement, et cetera, the way that I can kind of summarize it being that here in Westlake, we are on the west side of Cleveland. But if we go that way, we're traveling east. Right? We can be on the west side of Cleveland, but still going in the east direction. Same thing with position and displacement. You can be on the positive side of the origin, but traveling in the negative direction, or vice versa. Okay? Good there. That's what's summarized here at the top of page 46, and also I believe at the top of page 3 of your packet. Delta x, displacement, is positive when the change in position is in the positive direction, regardless of where you are in relation to the origin. Delta x is negative when the change in position is in the negative direction, regardless of where you are in relation to the origin. Good there. All right, last thing for this section, as the bottom of page 46 realizes, or shows you. Distance and displacement are not the same. First big difference that we just discussed earlier in this period is what? Let's use 2 words. What's the first word called? Scalar and vector, right? So, one's a scalar, one's a vector. Distance only tells us magnitude, displacement tells us magnitude and direction. Okay, so that's the big difference. Sometimes that means they're different. Other times, it really doesn't make a difference. Okay? Let's talk about way back at the beginning of the first page of chapter 2, which I think page 42, if I remember correctly. There's a picture of guys running a race. Okay? 100-meter dash. Distance traveled by the runners would be what? Distance traveled in a 100-meter race would be 100 meters, right? Displacements of runners in a 100-meter race. We could probably go with positive 100 meters, assuming we call that direction positive, right? Technically, it could be negative 100 meters, depending on what direction we call positive and what direction we call negative. It probably makes the most sense to call that direction positive. Okay?
Are we determining positive and negative?
Yes, at this point, because in one direction, or sorry, in one dimension, right, we only have two options, right? So you either have right or left, okay? All right, 200-meter race. Distance traveled during a 200-meter race would be 200 meters. Is the displacement 200 meters?
Why not? I guess you have to know a track.
You do have to know a track in order to understand. Sorry, does everybody know what a track looks like? All right.
I just don't know how much it is.
So now you don't have to give me an exact number, but right. The question I asked you was, is the displacement 200 meters in a 200-meter race? That's zero.
You don't know that to do it?
That's 400.
No, I don't know anything.
Sorry.
I know what a track looks like, but
I don't.
isn't it final?
Okay, so one lap around the track is 400 meters. Okay. The first example we talked about. Let's see if I have. Everybody see an arrow up there?
Yeah. Next to the star.
Alright, so it's not really the arrow I was looking for, but that's okay. But you found it though. So. Alright, so a 100-meter race. Okay? Anyway, so a 100-meter race, we talked about the distance and the displacement are both 100 meters. 100 meters positive for the displacement. Okay? In a 200-meter race, we're going to start here, run like this, and end up here. So we talked about in that case the distance is going to be 200 meters, but you told us earlier that displacement depends on two things. What are the two things that displacement depends on? That's how we define displacement. How do we calculate the displacement? Final and initial. So here's the final position, right? This is x final, and here's the initial position, right? Is that 200 meters? No, it's not, right? Because the long way around is 200 meters. That's going to be less than 200 meters. Okay? Last one, right? 400-meter race.
Wait, no, I don't. What's the displacement then for that one?
We can figure it out mathematically. Right now, the only thing I want you to know is that it's less than 200 meters.
I don't get why.
Do you get that
Because it's final minus
this is 200 meters?
right?
Okay, because that's a 200-meter race, right? But when we talk about displacement, we're only concerned about the distance between where we started, sorry, should be distance, okay? The difference between where we started and where we finished. You start here, you finish here. Is that 200 meters from here to here?
No, so
No.
we don't go around.
Remember, when you're talking about displacement, it doesn't matter what you do between the start and the finish, right? When you go out on Friday night, it doesn't matter what you do from 6:30 p.m. until midnight when you get home, as long as you start and end at the same spot. Don't take that literally.
But how did, like, why can't it be like a squiggly line? Like, how do I know it's just like a, I just,
The point being, it
what's
doesn't
the point?
matter.
Oh,
When you're talking about displacement, it doesn't matter which path you take. Let's say this runner goes from here to here, right? And then this guy, for some reason, goes this, goes here, goes to the infield, goes to the curling cue, right? In both cases, the displacement is the same because they both start and end in the same spot. Anyway,
Okay, can you draw a dot where the 100-meter would end?
the height. 100 meter, sorry. The arrow represents the 100 meter, okay?
There's no
So this is x initial for the 100 meter,
Okay.
okay? And this is x final for the 100 meter.
So that's why it's just do dots.
Right. The point I'm going to get to this being, distance and displacement are going to be the same as long as what?
As long as it's you're going one line.
As long as it's the same direction, right? One line. Okay? Because we can't just say one line. Because if I start here, run halfway, and then go here, right? The distance of this is 100 meters, but the displacement would be, see,
So when it's a straight line and you're going in the same.
as long as you're going the same direction,
Same direction.
distance and displacement will be the same. But as soon as you change directions, now they're different. Yep. Do we have to do the 400 meter race, or are we good with the
No.
400 meter race? All right. Good. Okay. On page 3 of the packet that I gave you yesterday, there is, in the middle of the page, a rough drawing of a class or a school, which apparently doesn't have very many classes because they have the library, the physics classroom, the math classroom, and the music classroom all in exactly the same hallway. So, I don't know where it is, but it's not a very big place. So, to the left of those pictures, where it says figure 2.4, I have taken some of the words out of that description because I want you to fill in the words. Okay? Underneath those pictures, quick example 2.2 and practice problem 2, all 3 of those problems deal with that picture. So let's take a couple minutes, talk to the person next to you. If you have your book open, you want to push your book, the answers are right there. So. But talk to the person next to you if you need to, and let's use this picture of these people walking into school and the coordinate system that was given to you to fill in the blanks underneath figure 2.4. Answer quick example 2.2 and practice problem 2. Take a couple minutes, go.
I didn't do that one. I didn't. Oh, I was doing this one. I was doing this one.
All right, let's jump in. So, class recording has begun again. I paused it while you guys were working on that. So, answers to these 3 problems are up on the board. I drew them in different colors, so hopefully you can figure out which one's going on where. So, in the first, okay, take a look. Any questions? Any that we didn't get? Sorry, can you see the bottom? Negative 8, 20. Good there? All right. So, if we take a look at the calendar for tonight, so our plans and then the homework for this evening. Homework for this evening is 6 problems, similar in nature to the problems that we just did on the board. Some of them are conceptual, asking you kind of about like, hey, is the distance the same as the displacement here, blah, 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 blah. And then some of them are numerical, very similar to the problems that we just did. Okay? So at the end of chapter 2 assessment, page 66, number 46, number 51, 52, 55, 58, and 59. I think I told you, I mentioned this to you before, but just in case you don't remember, one of the cool things about your book is that they number the problems numerically from the start of the chapter to the end of the chapter. So there is only one question number 52 within chapter 2. So if it says chapter 52 or chapter 2 question 52, there's only one question. And then down at the bottom where it says attachments, there are the answers to those problems. So you can check out and see how you did. Just say again? Yeah, homework. So we will go over this tomorrow. Like I said, Jason, I'm not going to collect it tomorrow, but this is the kind of stuff that's going to show up on your quiz, like on Monday. So. Good? Questions? Enjoy that homework assignment tonight, and see you guys tomorrow.